Let's look now at section 2.8 and talk about the algebra of functions. So whenever you have an equation that defines a function, say for example f of x is equal to x squared plus 5, you can substitute values directly into this function. You can say, okay, change the argument, change this x to a 4, and that would mean, well, this value of x would also become a 4. You can evaluate a function by substituting a number into the argument, and that gives you a specific value for your variable. Right? Other functions, however, work separately. So, for example, if I were to have another function g of x, and that would be, let's say, for example, 3x minus 4. This would be a separate function. If I wanted to substitute in a value like 6, I could substitute it in here, and that would be 3 times 6, and then minus 4. I can do that separately over here, 6 squared plus 5. And I would get two separate answers for two separate functions that are unrelated. But just like numbers and variables and expressions that can be combined, that can be added, subtracted, multiplied, and divided, functions can be treated in a similar way. We can take functions that are separate and combine them together in different ways to form new objects, to form new functions. So let's take a look at 5 different ways of combining functions together. The first 4 are going to be very, very familiar. You're going to pick them up fairly quickly, mostly because they're ones you've seen since, well, you can probably remember. Those are the basic operations: addition, subtraction, multiplication, and division. The last one is going to take a little bit more detail because it's one that's a little bit new, that's specific to functions. So let's go ahead and consider 2 functions. And let me go ahead and do that down here. Let f and g be functions. Okay? Doesn't matter what functions in particular they are, just let's have them be functions. This is a definition, by the way. Definition. So let f and g be functions. We can define 4 new functions which are created by combining 2 previous functions in a unique way. Here, the first function is going to be called f plus g of x. And that is made in, well, hopefully the most obvious way possible. If I want to create a function called f plus g, the way I should do that is by taking whatever f is and then adding whatever g is. So the function f plus g is made by taking f and adding g. It takes no imagination to realize what the other ones are going to be. If I have f minus g of x, a function called f minus g, well, you expect that to be made by taking the function f and subtracting the function g. And that's exactly the correct way to do it. So for example, up here, I'm not done with these yet, but let's look at an example of these so far. If I have these 2 functions here, if I wanted to find f plus g of x, that would be made by taking f of x, which is not some mysterious function. It's this function that we have right here. It's x squared plus 5. Y equals x squared plus 5. Here, we're going to add g, which is 3x minus 4. Y equals 3x minus 4. Like that. And now we can actually add the way we usually do. We'll combine like terms. Here we have x squared, 3x, and then 5 minus 4 will just give us plus 1. Subtraction works the same way. We have f minus g. We would start with the function f and subtract the way the function defined is g. And so that'll give us x squared minus 3x. And that's 4 minus a minus, so that'll become plus 4, which will give us 9. 5 plus 4, which will give us 9. Okay. The next 2 that we're going to be looking at are f times g of x. Okay. And that's made by taking whatever function we're calling f and multiplying it by whatever function we're calling g. Depending on the notation, some people will write this as f times g with a little dot in the middle. Other people will just write fg. The two functions names next to each other both mean the same thing. What you don't want to write is f and then a little x with a g there. Yeah, the little cross is sometimes used as a multiplication symbol, but then that's going to start getting confused with this x. So if you are going to write a symbol in between, you should use a dot. If not, well, then you can just write fg. Either one of those is correct. The cross is maybe not the best idea given the context. And finally, f over g of x is made by, well, taking f of x and dividing it by g of x. Okay. Up here, we would have f times g. And again, based off of our definition, that's the product of whatever we're calling f times g. And so now we multiply the way we always multiply. Let's distribute. X squared times 3x will give us 3x to the third power. And then x squared times minus 4, well, that's minus 4x squared. And then 5 times 3x will give us 15x. And finally, 5 times negative 4 is negative 20. And there we go. That's a new function. Notice this is a different function. Y is not equal to x squared plus 5 anymore. And y is not equal to 3x minus 4 anymore. Y is now equal to a completely different thing. It's equal to 3x to the third minus 4x squared plus 15x minus 20. But this function is not completely unrelated to the one we had before. Rather, it's made by multiplying the rules for the two functions that we started with. So this is a new function, but it's made by combining two old ones. And finally, we have f over g of x. And again, that's made by taking your f and dividing it by your g here. All right, and we can divide those out. Here, I'm going to leave that like that for right now. We actually can divide that out. However, it may be a while since you've seen long division of polynomials. And this is something we're going to look at more closely in the next chapter. This is the end of chapter 2. We're going to look at division of polynomials again in a lot of detail in chapter 3. So here, this wouldn't quite be done. We could divide this out a little more, but it does require you to perform division of polynomials. And again, we'll review that in the at the beginning of the coming section. At the beginning of the coming chapter, chapter 3. Okay. Now, one thing you'll remember about functions is that they have a domain and a range, meaning there are numbers that you can substitute in and ones that you cannot. Well, okay, but if I just made a new set of functions out of two old ones, what are the domains of these new functions? Are they the same as the old ones? What if the old ones have different domains? What if this one had a domain of all the positive numbers and this one only had a domain of all the negative numbers? How does that work? So here, along with our definition of how we define these four new functions, we also have to talk about their domains. Fortunately, it can be summarized. We don't need 4 different rules. It can be summarized with just one statement. The domain of these functions is the intersection of the domains of f and g. When we say the intersection, that means the overlap. So where do these overlap? So if f is defined for every number between 0 and 100, and g is defined for every number between 50 and 200, the overlap would be all the numbers between 50 and 100. Right? So the domains of these functions are made by the overlap. Wherever, if one of them is defined but not the other one, well, then you can't combine them because one of them doesn't exist. If neither of them exists, well, then you definitely can't combine them because neither one exists. In order to combine them, they both have to exist, meaning you have to be in the domain of both. So you want to find where the domains overlap. The only other thing we have to consider is right here. There is one last thing that isn't covered by this statement, and that is, well, remember, that's a fraction. And with a fraction, you can't have a denominator equal to 0. So here the domains of the functions, the domain of these functions is the overlap of the domains of f and g. And one last thing, for this fourth function, f over g, we also have the condition that g of x should not equal to 0. Because again, dividing by 0 is undefined. So for that one, let's go ahead and consider another example. We're going to do something like this, where we're going to combine some functions. But here, now let's talk explicitly not just about how to combine them, but also let's mention the domain and the range of these. So let's see here. Let's say we have a function f of x is equal to the square root of, let's say, 1 minus x squared. So that's a function. Well, f of x equals to the square root of 1 minus x squared. And let's say I have g of x, which is equal to just x. That's sometimes called the identity function. All right, whatever this is identifies this one. This one's identically this one. All right. Y is equal to x. So now let's go and start combining these. Although I guess even before that, the domains of the functions that we get by combining these two will be the overlap, the intersection of their domains. So before we even start combining, let's say what their domains are. So this one, well, the domain is every real number. Recall from a previous section that the domain of a function is everything except for whatever makes a denominator 0 or whatever has us taking the square root of a negative number. Here, we don't have either of those. Here, you're not dividing by 0 ever because there is no division ever at all. And you're never taking the square root or the fourth root or the sixth root of a negative number because, again, there's no roots here. So this has every real number as its domain. The same thing is true for these. Up here, these have every real number in their domain because, again, there's no division by any number here, so there's no way you're dividing by 0, nor do you have any roots, square root, fourth root, sixth root, or anything of that nature. Generally speaking, anytime you have a polynomial, if you have a function that you define as a polynomial, the domain is every real number. Because, again, polynomials only have addition, subtraction, multiplication, and powers. You're never dividing by a variable, and you're never taking any roots. So same thing is true for this one. So the domain of this one is all real numbers. Okay, from minus infinity to infinity. Okay, let's talk about this one. This one doesn't have a denominator either, so we don't have to worry about division by 0. But what this does have is a square root. And remember, with a square root, you have to exclude whatever makes the radicand, the stuff inside the square root, the radicand, less than 0. Okay, so let's go ahead and do that. Remember, we have to exclude, we have to throw away whatever makes 1 minus x squared less than 0. Okay. Now, in previous sections, 1.7, I believe, we talked about inequalities. However, in those sections, we talked about inequalities that were linear. This might be the first time we've seen an inequality that's not linear. In later sections, we'll talk about more complicated inequalities, including ones that look like this. And you say, well, if we haven't talked about how to do that, how do we do that now? Well, for now, what we can do is we can use a graph. Because even though we haven't talked about the algebra of these, we know what the graph of this looks like. So let's see here. If I was going to graph y equals 1 minus x squared, I'm not worried about the square root, just this part right here. Well, we're going to start off with the parent function, which is y equals x squared. If you ignore all the pluses and the minuses and times and divides, this is basically just x squared. And we know the parent function of x squared. It looks like this. Okay, but now that x squared isn't an x squared. It's a minus x squared. Oh, okay, so it's being multiplied by a negative. All right, the whole function, the whole x squared has been multiplied by a negative. And as you remember from our section 2.6, whenever you have a parent function that's multiplied by a negative, the whole thing does what? It flips upside down. So this is our parent function. And now, with that negative in front, it flips upside down, like that. And finally, we have an extra plus 1 right here. Now you might say, well, no, that's not plus, that's minus. Well, no, the negative is part of the x squared. This 1 is a positive number. You could also think of this as minus x squared plus 1. Okay, so if I'm adding 1 to a function, it's going to pick it up one step. So now this would come up from 0, 0 up to 0, 1. Okay, so if you're looking at that graph, what you want to do is you want to exclude, you want to throw away whatever makes this less than 0. Well, less than 0 means it's below the x-axis, right? So that's all of this stuff over here. So let's throw that away. And that's all this stuff over here. Let's throw that away. So this is 1 minus x, y equals 1 minus x squared. And we want to exclude, we want to throw away whatever makes this less than 0. Well, your y value is equal to 0 at the x-axis. So if I want that to be less than 0, that's all this stuff down here. Okay, so throw it away. So whatever's left is what we want to keep. Right here, what's left is everything from minus 1 up to 1. In later sections, we'll talk about how to do that completely algebraically. We won't need to worry about the graph, but for now, this is good enough. So here, we're going to exclude all that stuff, which means we're going to include the stuff between minus 1 and 1. Okay, so here the domain of this function is everything from minus 1 up to 1. We're excluding everything below the axis, which means the points at the axis, right here at the x-axis, those are included as part of our domain. So that's okay. Everything from minus 1 to 1. Okay, so that's our domain. Remember, for any polynomial, the domain is all real numbers. There's not really any extra consideration you have to do there. However, here, because that has a square root, we needed to throw away everything that made the square root negative. So we kept all the stuff that's above and on the x-axis, which is everything from minus 1 up to positive 1. So now let's go ahead and combine our functions. And I'm going to go ahead and do this. Let's do this 2 different ways. We'll do it with addition and we'll do it with division. First, let's find f plus g of x and the domain. And then we'll do the same thing for division. All right, so f plus g of x. Remember, f plus g of x means you want to take your f of x and add your g of x. Okay, so there's your f of x, there's your g of x. Let's stick a plus sign in between them. There we go, all done. And now, to find the domain, we want to find the overlap between these 2 domains. Oh, well, this is all real numbers. So if I visualize that, that's the entire number line. And here, this is the numbers between minus 1 and 1. So where do those overlap? Well, between minus 1 and 1. After all, this is the whole number line. This is just a little piece. So where do they overlap? On that little piece. So here the domain of f plus g of x is the same as the domain of the function f. It's from minus 1 to 1. Just like that. Let's go ahead and try to find f over g of x and the domain. I guess I should say and its domain. Okay, so again, f over g means take your function f, which is this one, divided by your function g, which is this one. So that's going to be f over g of x is equal to the square root of 1 minus x squared over x. Okay. Now, the domain is going to be the overlap between the domains of f and g, which again, as we just saw, is between minus 1 and 1. But with division, there is one other consideration, and that's that we have to throw away whatever number makes the denominator equal to 0. Okay, so here the overlap between the domains of f and g are the values between minus 1 and 1. So this thing right here that I've illustrated from the previous part of the example. But now, because this is division, we also have to throw away what makes the denominator 0. In this case, you're throwing away the number 0. Right? If you plug in 0, that denominator is 0 now. So we want everything in this interval, but for division, we throw away one last thing, and that's whatever made the denominator 0. Okay, so now for this one, my domain is slightly different. It's very similar, but now I also have to throw away one more point. I want everything from -1 up to 0. Don't include the 0. And then we're going to jump over that point, which we're throwing out. And then we're going to take all the numbers between 0 and 1. And there's our domain. So go ahead and give this a try. Let's say you have a function f of x, which is equal to the square root of x plus 2. Okay? And let's say you have another function, g of x, which is the square root of minus x. All right? So those are your two functions. First of all, what you want to do is you're going to want to find their domains. Now, that's not the question here that I'm going to ask, but you do need that information to solve our question. The question is, find f minus g of x and its domain. And also go ahead and find f over g of x and its domain. Okay, go ahead and pause the video, give that a try, and whenever you're ready, go ahead and unpause the video and we'll go through it together. All right, so let's take a look here. F minus g of x. That's given by taking the function f and subtracting the function g. So we can write that as square root of x plus 2 minus that square root of minus x. And that's really about it. There's no like terms to combine. There's nothing else you can really do. That's the simplest way you can really write that. Okay, but now the domain. Well, what we need to find out what each of these domains are and find out where they overlap. All right, so let's go ahead and do that. The domain of this one and the domain of this one. Well, let's see here. We can either do this by graphing, because after all, the square root is one of our parent functions, or we can do it by solving an inequality. That is to say, x plus 2 has to be greater than or equal to 0. We want to exclude whatever makes x plus 2 less than 0. Likewise here. It doesn't really make a difference here. You can do it either way. So if you did it with a graph or if you did it with an inequality, you're going to get the same answer either way. So here, let me go ahead and just do it with, I guess I'll do a graph. You should have, no matter which way you do it, it does give you the same answer. So here, our parent function would be the square root function like that. Right? The square root of x has that graph. But now by adding 2 to the variable, we saw in 2.6 that adding 2 to the argument, to the variable of your equation, moves everything to the left by 2. It's opposite of what you might think. You would think plus is to the right. But remember, section 2.6, adding moves everything to the left. So that'll go to the left 2 steps. And it's still the same graph, just slid over a bit. So here, notice this starts at -2 and then goes forever to the right. So from -2 out to infinity. We want to include -2 as part of our graph. After all, that point 0, 0 was included in the original parent function. So when you slide it over, that point will also be included in your function f. And then for this one, we do something that's pretty much the same. Very similar. Here's your parent function. Y equals the square root of x. And now this negative is multiplying our argument by -1. From section 2.6, we remember that multiplying by a negative, that's going to cause a reflection. When the negative is on the outside, that reflects things upside down, but on the inside, it reflects things left to right. So our graph looks like that. Still touches the origin at 0, 0, but now instead of going up and to the right, it goes up and to the left. So the domain of this is everything from -infinity, because it goes off forever that way, up to and including 0. from minus infinity up to and including 0. So that is the domain of f, and that's the domain of g. So now the domain of this function has to be where these overlap. All right, well, let's see where that is. If I have a number line from minus infinity to infinity, from negative 2 to infinity, okay, that's starting from negative 2 going forever to the right. And now from negative infinity up to 0, that's starting from 0 and going forever to the left. Where that overlaps, well, that's all the stuff in here, between minus 2 and 0. So right here, that's going to be my function f minus g, and its domain is all the stuff from negative 2 up to 0. Just like that. F over g of x we find that by taking the quotient of our two functions. That's going to be the square root of x plus 2. That's our f. Over our g, which is the square root of negative x. There are some ways we can clean that up slightly. There are ways of simplifying square roots, products, and quotients. But here, this is good enough for what we're doing right now. So we've combined our functions to form one new function. And now when we consider the domain of this new function, it should be the overlap of the two old ones. Okay, so everything from negative 2 up to 0. Right, but we also have to throw away whatever makes the denominator 0. Oh, well, that's just the number 0. Because after all, if you take the negative of 0, that's still 0. So here, if you plug in x is equal to 0, that makes your denominator 0. Okay, so that's all of this stuff. Oh, but you do have to throw away the number 0. So go ahead and throw that one away. Oh, well, that doesn't change anything except that the 0 is no longer included. Okay, so our domain will look almost exactly the same. It'll be everything from minus 2 up to 0. But now the only difference is we have to throw away that number on the endpoint. You have to throw away that 0 because if you include 0, well, that makes your denominator 0. So it's the same domain minus the 0. So now you don't include it. And that's it. We find our new function f minus g with its domain, and we find our new function f over g with its domain. One thing to note about these functions, these new functions that we've created, they are functions in every way, shape, and form, and which means we can treat them like functions that we have before. For example, let me just go ahead and continue to use these right here. All right. Let's say I pick a number that's in the domain of both. Because if I don't, well, then something's going to happen that I can't handle. So let's pick a number that's in the domain of both of these. I'm going to go with negative 1. Okay? Here, that's just a number between negative 2 and 0. All right, so what is f of negative 1? Going back to just the original function f. Oh, well, the way that works is the x value is getting replaced by a negative 1. So that's going to be the square root of negative 1 plus 2. And that's going to be 2 plus a negative 1 is 1. And the square root of 1 is, well, it's the number 1. Okay, now let's find g of minus 1. Well, again, that just means go to your function g, and anywhere there's an x, you plug in a minus 1. Okay, so that's going to be the square root of a minus 1. Right, that minus comes from the function. This minus comes from the fact that you've plugged in a negative number. Okay, well, negative of a negative, that's a positive. And so the square root of a positive 1 is 1. Okay, so now, what happens if you were to take f of minus 1 and subtract away g of minus 1? Well, we know what f of minus 1 is. It's the number 1. Minus, well, we know what g of minus 1 is. It's also the number 1. And 1 minus 1 would give me 0. Okay, so right now what I've done is I've evaluated each of these functions on their own using a number. And then once I evaluated each of them on their own using a number, I took those answers and combined them. All right, now consider this function that we found just a moment ago, f minus g. Notice that negative 1 is in the domain of f. It's in the domain of g. Well, it's also in the domain of f minus g. So that means that Yeah, I can choose to plug -1 into this function or this function. I could also choose to plug it into this function. All right, so let's see what happens when I plug it into this function. If I have f minus g of -1, that means I'm going to take this and I'm going to plug in a -1 there and there. That's going to be square root of -1 plus 2 minus the square root of negative of a -1. And all that can be simplified. Here that's going to be the square root of 1 minus the square root of, well, also 1. And the number minus itself is 0. Notice two things. One, this is still a function. I can still treat it the way I always treat a function. If I want to plug in a number, I can plug in a number. No problem there. But the other thing that you should notice is that by substituting in the function into, by substituting in that number into this function, I get the same result as if I had substituted it into the two original functions and then combined those answers. Essentially what finding this kind of function does, what finding f minus g does, is it tells you the result of subtracting the two functions at any of their points. In other words, if I wanted to find f of 5 and g of 5, I could plug 5 into each of those. And then if I wanted to find out what the difference of those was, well, then I could find those two numbers and subtract them. Or I could just plug 5 into this one directly and be done with it. All right? So here, not only is f minus g a function, but it tells you the results of subtracting those two functions when you substitute in a value. The same thing is going to be true of all of our other functions. This f plus g, this f minus g, f times g, and f divided by g, they're all functions. They're going to work the same way functions always do. But on top of that, they're going to tell you what happens when you take values of f and add them to values of g without ever actually having to add them. Notice up here, I found this function without ever knowing that I was going to plug in the number -1. That happened after the fact. Now, there is a fifth way of combining functions. We've seen addition, subtraction, multiplication, and division. And in spite of the fact that we have to now worry about domains, and there can be some subtle changes between them, essentially, this isn't too different from things that we've seen in pre-algebra. Because, yeah, we may now be talking about functions instead of expressions, but we're still just adding. We're still just subtracting. We're still just multiplying. We're still just dividing. So in spite of some new considerations, not much is different from before. But now let's take a look at a fifth type of operation, which is a little different from what we're used to. This will be our last kind of operation. It'll be different from addition, subtraction, multiplication, or division. This is called composition. So let's go ahead and define what we mean by that. Again, we're going to start off with two functions. So let f and g be functions. And they'll have their own domains, which we'll talk about here in just a moment. So let f and g be functions. The composition of f and g is given, first of all, the symbol that we use looks like this. It's going to be f of g of x. Compare that symbol to the symbols we've had before. We have f plus g, f minus g, f times g, and f divided by g. This one is read as f of g. So that little circle is read as of. A quick word of warning. People will confuse this for multiplication all the time. Notice this is a dot. This is a circle. They are similar, but they do not mean the same thing. F of g is a composition. F times g is multiplication. You say, okay, so they're different, but what is this one? I mean, I know what multiplication is. What is this? So f of g of x is given by f of g of x. At this point, you say, well, you just repeated yourself, right? F of g of x is f of g of x. You just said the same thing. Right. But notice that when we write it here, it becomes a little different in the notation, and hopefully this difference makes it a little clearer what a composition is. Remember how function notation works. Whatever's in the parentheses, that's what you're plugging in. So by writing f of minus 1, that's telling you minus 1 is getting plugged into f. By writing g of minus 1, you're telling someone that negative 1 is getting plugged into g. Whatever number's here, that's what's getting plugged into your function. If I change the number, if I said f of 5, then I'd be saying 5 gets plugged into f. If I said f of 100, I'd be saying 100 gets plugged into f. Well, here what I'm saying is f of g. Notice that that's the same notation. This negative 1 in the parentheses is what's getting plugged into f. But now over here, what's in the parentheses is not a negative 1 or a 5 or a 100. It's a function g. Oh, but given the notation, it's what we're plugging in. F of g of x means take the function g and plug it into f. That's what makes this a little different. We have only just started talking about how to substitute in numbers into functions, and all of a sudden we're going to be substituting in things that are functions into other functions. This may sound a little strange at first, but it's actually fairly straightforward because we are plugging things in a way that we're used to. By which I mean we're going to be substituting. Before we do an example, I mentioned a domain here about f and g. So here, let's go ahead and finish off the definition by talking about the domain. Here's how you find f of g. You plug one function into the other. The domain of f of g is all real numbers, in the domain of g for which g of x is in the domain of f. Like that. Okay. What does that mean exactly? It'll become a little more apparent through our examples, but essentially what this is saying is we're plugging one function into another. So the domain has to pass through two different functions, meaning, okay, if I'm going to plug an x in, that x is going to go into g, because that's how this notation works. Now, that x should be part of the domain of g. If it's not, well, then we can stop. The whole thing's broken from the very first step. Okay, but let's say that x is in the function function's domain. Let's say it is in the domain of g. Okay, well now that's not enough, because now whatever result we got from this, that result has to be plugged into f. So here, x has to be in the domain of g, but once you plug it in, that result also has to be something that can be plugged into f. This will become a little more apparent through our examples. So let's go ahead and do some of those. Let's begin with a couple of functions. Let's say f of x is equal to x squared minus 3x. And let's say g of x is equal to 2x plus 5. Okay, so here are our two functions. Let's go ahead and compose them. Remember, that's the word, that's the phrase, composition. When you find the composition of something, you compose them. So here we can say compose f with g. You can say find the composition of f with g. But we usually don't write out full sentences. Usually we use the notation that we've been given. So yeah, you can say compose f with g, find the composition of f with g, but more often you're going to say find f of g. and all three of these mean the same thing, this notation is often shorter. All right, so let's go ahead and do that. We're going to find f of g of x. We'll talk about the domain afterwards. Okay, so f of g of x, that means find f of g of x. And even though the words that I just said are the same, the way I've written it makes this one a little clearer as to what order I want to do things in, meaning what do I want to plug into where. Well, the way function notation works, whatever's in the parentheses is getting plugged into the function. So here, I'm saying I'm going to take the function g and plug it into the function f. But I don't have to be so mysterious about it. I don't have to say the function g, because I know what g is. It's equal to 2x plus 5. So here, when I say I want f of g, I could be a little more specific. I could say I want f of 2x plus 5, because that's what g is. But now, what I'm saying is I want 2x plus 5 to be plugged into f. Okay, well, what's f? Well, f is this function up here. Which function? Well, it's the function that says whatever you're plugging in is going to get squared. And also whatever you're plugging in is going to be tripled. And then we're going to subtract those two from each other. Okay, so f is the function that says whatever you plug into it, it's going to get squared. And then whatever we plug into it, it's going to get multiplied by 3. And then we're going to subtract. All right, f says whatever's getting plugged in, squared, minus 3 times whatever's getting plugged in. But from our notation, we can see that what's being plugged into f is 2x plus 5. So here, that's going to be a 2x plus 5, and that's going to be a 2x plus 5, just like that. Oh, but now I can simplify. I can actually just multiply this stuff out and combine like terms. So let's do that. 2x plus 5 squared, that means 2x plus 5 times 2x plus 5, which is going to be 4x squared plus 20x plus 25. Right. If you don't see where that's coming from, write down 2x plus 5 times 2x plus 5 and then do your distribution. Right. Same thing here. We're going to distribute. We're going to multiply this out. Negative 3 times 2x, that's a negative 6x. And negative 3 times 5, that's a negative 15. And now you see some like terms that you can combine. So that's going to be 4x squared. You have 20x minus 6x, that's going to be 14x. And then 25 minus 15 is 10. And there we go. That's the composition f of g of x. Now, one thing to note, and that's compositions can be done in either direction. And that does not mean you're going to get the same answer. Here, we found f of g of x by taking g and plugging it into f. We can also go the other direction, find g of f of x, which is to say take g of f of x. Or in other words, plug f into g. When you compose functions, changing the order might give you the same answer, but it doesn't have to. You can have the composition done the opposite way and get a completely different answer. Depends on the functions. So here, we're going to take f and plug it into g. Okay, well, what's f? Well, f is that thing right there. It's x squared minus 3x. Okay. So g of f means g of x squared minus 3x. But now g is the function that says whatever you plug into me, I'm going to go ahead and double it and then add 5. Okay, well, here's what we just plugged in. So g is going to double it and then add 5. All right, g is the function that says whatever you plug in gets doubled and then we add 5. Whatever is plugged in gets doubled and then plus 5. But now here, that's what you're plugging in. Okay, so let's go ahead and double that and then say plus 5. 2 times x squared is going to be 2x squared. 2 times negative 3x is negative 6x. And then don't forget your plus 5. And notice that both of these are quadratics, but they're definitely not the same. Right? That's not to say they're going to be completely unrelated. It's unlikely that they're going to be totally different, but they definitely do not need to be the same. So be mindful of that. Composition, it does matter what order things are in. So make sure you do things in the correct order. Now for these particular problems, the domain is very, very simple. After all, this is a polynomial. Its domain is all real numbers. This is a polynomial. Its domain is all real numbers. So when we ask for the domain of a composition, we say we want all values, all real numbers that are in the domain of G, for which G of X is in the domain of F. If it's not in the domain, if it's an X that's not in the domain of G, or if it's an X that gives us G of X that's not in the domain of F, those have to be thrown out. Well, here we don't have to worry about that at all, because here these functions are defined for any and all real numbers. So in other words, it doesn't matter what X is. Here, you could plug whatever number you want into G, because G's domain is infinite. It's every real number. Oh, but then when I plug a number into G, it's going to give me some answer. Well, it doesn't matter what answer that is, because whatever it is, it can be plugged into F. Because again, F has an infinite domain from negative infinity to infinity. And likewise over here, if I start with f of x, well, I can plug anything I want into f. Right? If I plug in anything I want into f, that's fine, because the domain is from minus infinity to infinity. It's all real numbers. And once I plug whatever number I want into f, that's going to give me an answer. But it doesn't matter what that answer is, because whatever it is, I know I can plug it into G, because anything can be plugged into G. So here, yeah, we can discuss the domains of these compositions, but it's not particularly interesting for these problems because the domain is all real numbers. That's going to be the case whenever you compose polynomials, or really whenever you compose something that has a domain from negative infinity to infinity. So here, the domain is from minus infinity to infinity for both. So let's give one more example that involves functions that are not going to do that, where we actually do have to worry about the domain. So let's consider two functions. F of x is equal to x squared, and let's say g of x is equal to the square root of x. Okay. Let's find the composition of these. Let's say I want to find f of g of x. And actually, you might try this one. Go ahead and pause the video, find the composition. Make sure you do it in the correct order. F of g is different from g of f. So f of g of x, that's going to be like this first one we did. And once you're done, consider the domains. These are both parent functions. You know their domains. If you don't remember, turn back to section 2.6 and look that up. Right? Think about what their domains are, and think about the domain of what happens when you compose them. Go ahead and pause the video and give that a try. And when you get an answer that you are happy with, go ahead and unpause the video and we'll go through it together. Okay, so f of g of x means f of g of x. All right, well, that means I'm going to take g of x, which is the square root of x, and I'm going to plug that into f. Okay, well, I know what f is. F is a function that says whatever you plug into me, I'm going to go ahead and square it. Okay, well, here's what we plugged into it. So now f is going to take it and going to square it. And we can simplify this. We can say the square root of x squared, well, the square and the square root, that's just going to give us x. Okay, so we find the composition f of g of x, and that gives us just x. Okay, so now let's talk about the domain. Now, at first, it might look like the domain is all real numbers, because after all, I have a result that is just x. That's a polynomial. Y equals x, right? That's a linear equation. And as we've seen, every linear equation, y equals x, or mx plus b really, is going to have an infinite domain. Anytime you have a polynomial function, it's got an infinite domain. But that's a little misleading, because right now what we're looking at is the result of the composition. What we want to look at is the process, not what did we get at the end, rather how did we put these together to get this at the end. Here, in order to compose these, we plugged g into f. What that means is whatever x value we choose to plug into this new function, this composition, has to go into g first. Only once it gets through g can it be plugged into the next function, f. But that's where we run into a problem, because remember, g does not have an infinite domain, or rather, it's not all real numbers. It goes from 0 to infinity. The domain of the square root function is all numbers from 0 to infinity. The domain of x squared, okay, that is a polynomial function, so that's all real numbers, from minus infinity to infinity. But now, if I'm trying to substitute in a number into my composition, it first had to go into g. And you notice not all numbers can do that. In fact, only positive numbers, or 0, can be substituted into g. So yeah, it's true the second level of the composition can accept any number, but there's going to be a bunch of numbers that are never even going to reach that level because they did not fall into the domain of the function g. So here, our domain is only going to be the numbers between 0 and infinity. Even though this is a polynomial, and normally polynomials would have an infinite domain, because this polynomial came from the composition of two things, and one of these functions that was composed did not have all real numbers as its domain, then that's going to cause a restriction to this result. If that doesn't quite make sense, if you're not quite sure why we're limiting some, let's go ahead and plug in just a couple of numbers, which hopefully will illustrate why that is. Let's say I wanted to find f of g of 2. Let's say I wanted to find f of g of, let's see here. Let's say 9. And let's say I wanted to find f of g of minus 1. Like that. Okay. Here, let me make this a nicer number. Let me say 25, because otherwise I'm going to be dealing with less pleasant numbers. All right, so here we go. F of g of 25. Well, the way compositions work, first this 25 gets plugged into g, and then that result gets plugged into f. Okay, well, let's do it in order. If you plug 25 into g, that'll give me the square root of 25, which is just the number 5. So here, f of g of 25 is really just f of 5, because g of 25 is the number 5. If I plug 25 into g, the square root of 25 is 5. Okay, but now f of 5, well, that means I'm plugging 5 into f. Okay, so 5 squared is 25. Okay, cool. No problem. If I plug 25 into this composition, I get an answer. No problem. Let's say I did 9. Okay, so that's going to be 9 goes into the function g. So I take the square root of 9, which is the number 3. G of 9 is equal to 3. So f of g of 9 is f of 3. Notice how compositions work. You're just going from one function to another. The result of one or plug into another. Okay, well now f of 3, that means I plug 3 into f. Okay, so 3 squared is 9. All right, no problem. Okay, let's see f of g of minus 1. Well, first of all, we'd have to plug negative 1 into g. Oh, but now I'm done. I'm stuck. Because remember, the domain of the function square root of x is only made up of positive numbers. By trying to plug negative 1 into g, that's it. I'm done. This is undefined. All right? If this number doesn't fall in the domain of g, then g is undefined at that point. Oh, but if it's undefined here, well, then I don't get an answer to plug into f. F is perfectly happy to accept any number. but G doesn't even give a number for me to plug into F. So here, this one would be undefined. Not because F had a problem, but because G didn't provide any answer. I couldn't find G of minus 1, which means there was nothing to plug into F. So here, this restriction causes us to have this composition have a restricted domain. And that's it. That's it for the section. If anybody has any questions, comments, problems, please let me know. And I hope you all have a nice day.